We're going to be looking at the activity on our analog devices wiki, and this is for the heartbeat measurement circuit. So we have all of this, and the link for this will be in the description below the like button. We have the objective, and the objective of this activity is to learn how to use a chain of amplifiers for gain and filtering in a practical example that aims to recover heartbeat information. The result of the system provides a relevant output that is displayed using the scope tool. We're going to be using the Digilent Analog Discovery 2 for this. Going through this lab activity, the students will learn how to drive an IR infrared LED and a phototransistor. They'll be able to design and understand the behavior of a low-pass filter and explore functionalities provided by the op amps in different configurations. Combining the previously mentioned electronic devices, the result of the activity will demonstrate how a real-world application can be implemented with minimum software and hardware equipment. Now we go on to the background. A type of heartbeat measurement device consists of an electronic circuit that monitors heartbeat by clipping onto a fingertip. It does this by shining a light through the finger and measuring how much light is absorbed. This goes up and down as blood is pumped through the finger. For the operation as a optical heartbeat detector, a pair of infrared LED and phototransistor is used. The LED emits light through the finger and is detected by the phototransistor, which acts like a variable resistor, conducting different amounts of current depending on the light received. So whenever we get some light, or an increase in light, we get a kind of spike in current, and that's going to represent our heartbeat. The voltage variations change with the heartbeat and are required from the collector of the phototransistor. The small signal obtained is used as input for the circuit, obtaining the behavior of a heartbeat detector. In order to have relevant output, the input signals pass through multiple circuits. So first we have a preamplifier. The output signal from the heartbeat measurement setup is decoupled through the series capacitor and amplified using a negative feedback resistor R4. We then have a low-pass filter, and it's going to cut the high frequencies. We just want the low one, so we're not going to have any noise in here. We then have a voltage follower that buffers the output of the low pass filter and reproduces its voltage with a low impedance output. We then have an inverting amplifier with low pass filter, amplifies the voltage signal and cuts the high frequencies, which is noise. We have all these materials, and we need these materials to use this. And we're also going to have another link in the description. It might not work, but it'll be a downloadable PDF of the links. We'll have all this, it's going to look like this, where we have all of these parts, and then we could click a data sheet for it. So I'll try to link the actual data sheet. This is not what we're going to be using. We're going to use the OP484, so we can just do find an OP and then a 484. It's going to take us to right here, so we can click on this data sheet. And I'll try to include this data sheet in the description. So that should be down there. Now we're going to look at the directions. So we're going to have our breadboard, and we're going to make this. This is kind of like a SPICE simulation where we have our OP284. Well, it says 284, but we want a 484, including the standard set of LT SPICE models. My partner did this in the lab, so I didn't do any of the SPICE simulations. I'm going to be doing the breadboard. Now for infrared LED. In order to have a proper current that will not damage your infrared LED, a resistor needs to be added in series to limit the current. Varying the value between the operating range will change the intensity of the emitted signal of the infrared LED. The following formula expresses the value of the forward current IF through our LED based on the positive voltage supply, which is plus 5 VP, series resistance R1, and forward voltage drop on the LED. So we can use this to figure out our current. We then have our phototransistor. So to acquire information from the phototransistor when it is in contact with the infrared light, a common emitted amplifier circuit is designed. The circuit generates an output which transitions from a high state to a low state when light in the infrared range is detected by the phototransistor. The output is created by connecting a resistor, R2, whose value is determined experimentally, between the voltage supply and the collector pin of our component. We then have our preamplifier. So the preamplifier is the input signal from the heartbeat measurement. It's set up and it's fed into a differential amplifier circuit. The capacitor blocks any DC content. We have C1 and R1 behaving as high-pass filters with the cutoff frequency of FC1. Besides filtering, the stage serves as an amplifier, taking the input current and generating at the output an inverted voltage based on the negative feedback resistance. We also have an active low-pass filter, and this is more information about that here. We then are going to talk about our final amplifier and the low-pass filter, and we are going to see this in our actual circuit right here. So this is the circuit, and I have built this on my breadboard. It's not going to be the exact circuit, and we'll see this in a moment, because there are some things wrong. The first thing that I did was, since both of my power rails goes all the way through, I had a jumper wire that connected this as the positive, and also this is the positive, so I don't have to stretch out these wires. So of course you want to have the resistor and on the side of the current flowing into the LED, so we limit the current flow, so it's going to go into the anode. So power goes into our anode for this infrared LED, and then it's going to go to ground. So we want to power and then ground our LED. Same thing for the phototransistor. We have power, we have our 1 kilo ohm resistor, and then it's going to the phototransistor, and then this other side is going into ground. Now the rest is going to be the same. There is an issue though with this capacitor. It's actually facing the wrong way. So the capacitor, the long lead, or the side that doesn't have the negative on it, should be facing the other way. So it should be going to the right, not to the left. So if we turn that around, then we should be okay. Now, I still have a problem with my circuit, so I'm going to actually go through and debug it step by step, and we're going to see this as well. Now we have the procedure that we are going to look at. Now, I didn't talk about this here, but we need to use a variable positive and negative power supply from this right here. It's a module. We want a 5 volts to power our circuit. So we're going to have 5 volts and negative 5 volts for our actual waveforms, and that's if we pause these and we look in our WaveGen 1, or not our WaveGen, if we look at our supplies, we have 5 volts and negative 5 volts. So that is important to note. We are going to use the scope channel 1 to monitor the voltage collector node over V output. That's this output right here, and we're going to look at that later. So we have output 1 right here, and then the other one's going to ground. So that is what that's going to look like. Here we have some important things in the simulation. We have the transient, which is going to connect the input of our circuit to the waveform generation source. And then we're going to configure the source to generate a sine with the amplitude of the following: 500 microvolts, frequency 2 Hz, 500 millivolt offsets, and observe the output signal amplitude in order to determine graphically the total gain of our circuit. So that is how we would do an AC sweep and find the gain of our circuit from this. We also have the equations above, and this is what our actual procedure is going to look like. So here we have my breadboard that I built. It's basically the same thing as the Digilant one that we have right here on the wiki analog. However, there's a few things that are different. The first is, like I said, the way we've wired the power. So I'll just put this right here. The way that we've wired the actual power into the infrared light and the phototransistor. It's wired like this, and we have a wire that goes across the entire way. We can see that this red wire and this black wire on the far right, they jump the actual current that goes through it so that we're able to use it. So now, if we look at our circuit here, we see that both of these are in the positive rails. That's going to go to power. We have the resistor for both of them going inside of there. And then we have our grounding wire going in here to ground. So the only thing that's different is that this blue wire right here, I've made it so where it's an orange wire and it's above this resistor. We could try debugging that to see if that makes any difference, and it goes straight into the capacitor right here. So with that, we have the rest of it pretty much the same. So this wire is going to go to here, which is the second pin. We have our 47 kilo ohm resistor that goes from the first pin into the third from the last pin here. We have this small, short little wire that goes out from the first, well, technically, because of the way that the op amp is. We have our input and output for this 2 and 3. So 2 is this resistor, and it's ground right here as well. So ground is going to go into this third pin. We have this resistor going to the second pin that's coming from the input, or the output, sorry. The first pin's the output. So we have output going this way into the black, into this resistor, going back into the op amp. So that's how that first op amp is wired. Next, we have this part of our circuit right here. So this whole part over here is like part 1. Now we take this resistor and connect our part 2. So it goes from the output of our part 1 to the input of our part 2. This red line right here and this black one up here up top, that's just powering our op amp, powering and grounding it. So that is the only thing that we're not going to look at. From here we have pins 5, 6, and 7. 5 and 6 are inputs, 7 is an output. So the output from our first part is going into the input 5. Then we have input 6 right here. It's negative feedback from our output. So that is how that would work. We have this little resistor. It's behind the capacitor. You can see it's right here. It's a 10 ohm or 100 ohm resistor, and it's going to go out like this. We also have a capacitor right here. Note the direction of my capacitor is facing. It's opposite from here. This is the correct way. This capacitor is going to act as a low pass filter. So we have it like this. It's going to go from the input here, and it's going to go to the same column as this ground right here. So we're going to go from this pin, the capacitor, and then we're going to ground it. Alternatively, we could just take our capacitor and then put it into our grounding rail, because this wire, this black wire right here, is just going to connect it to ground. There's nothing else left in this column. And then from here, so that's the change I'm going to make right now actually. I'm going to take out this black wire, and then I'm going to take the capacitor and I'm just going to put it into ground. That way it's a little bit simpler. We have one less wire in our circuit that we have to deal with. It makes things a little bit easier to see. Now this blue wire is really an orange wire in here. It's going to go from here into this part of our op amp, and we can see that 10, 9, and 8, we have our inputs and our outputs respectively. So 8, this last one, is an output, 10 and 9 are inputs. We now have our VN right here. This is the white wire, and that's the voltage negative that's coming from the power supply, the V minus. We then have our inputs, which are 10 and 9, and our output, which is 8. So we have 10, 9, and 8. Our input wire is this black one. It's going to be grounding it, so that is 10. Our 9 is going to be the input that we have from this orange wire to the bottom here. Now this input is also going to go this way. So I will move this over and zoom in a little bit so that we can also have the digilant up as well. So we have this wire, and it's going to go back to our capacitor and our resistor that's in parallel with each other. So we are going to have this go through here. It's going to end up right here. We could put it in the middle. That's how the digilant has it. So if we wanted to, we could just rearrange that on our board really quickly. I just did that now. Obviously you can't see it in real time in the picture, but that's how I did it. Now the next wire is this one, this orange one right here, that goes from our output. This last column is the output. So the output into the middle of these two right here. And that's going to be about it. This one's grounded. We have our V1 and V minus. This is our waveform generator, right? So we want to monitor outputs. We are going to ground the V minus. That's the white wire, or the yellow wire with the negative strip. And then the solid yellow wire is going to go into this column right here, where I have the orange one. So that's going to go right there. Now from here, we can see that we have another orange wire right here and another orange wire up here. Now these orange wires are going to be from our scope. It's the channel 1 positive and the channel 1 negative. So the channel 1 negative is the orange wire with the white stripe. We're going to plug that into ground. And then our channel 1 positive, we want to plug it into the same column as the output of our op amp, the last one, which is going to be right here. That way we can look at it and we can analyze it.
So I just moved some things around. What I did was I put this white wire below this resistor. I don't think that changes too much. And then I moved this capacitor just straight down to ground, and I put this orange wire in between the resistor and the capacitor. Now, then I plug in these two wires here. I move this orange wire from up here down on top of this resistor right here, And that way we can look at the channel. If we look at the analog discovery pinout, the channel 1 and channel 2, the channel 2 is going to represent our input, and the channel 1 is going to represent our output. That's what we're going to monitor here. And so if we go back to our waveforms, the settings I have are 0 volts, 1 volts for channel 1, 0 volts, 500 millivolts for channel 2. Our supplies is the same. Our wave gen, I've changed it to be a square wave, and 1 volt on the amplitude for this test right here. And we can see that we have some noise right here. We're going to eliminate that hopefully with the filters. And then we also have, right after this cycle, we have some strong input where it goes up like this. And that's it for all of them. Now, it is not perfect. We can see that for sure. If I put my finger over the infrared LED and the phototransistor, I'll do it in a second. But this is what it looks like without my finger on it. And if I were to put my finger on it, it would just look something like this. So not too much is changing. We can see that stuff is moving, but I'm not sure if it's just from my finger. So I've taken my finger off of it, and it looks like it is still changing without my finger. So it's not too big of a deal right now. We do have a lot of noise though. Hopefully we can clean this up though when we look at the next part of our circuit. So if I minimize this, we're now going to look at this part. So that's just debugging this first part. We get a result and it looks okay. So I'm going to stop this here and we're going to look at the next part.
We now need to test the next part of our circuit. Now, and by the way, I don't think I've mentioned this, but the reason why we have this yellow wire here is because if we look at our pinout, that's going to be our waveform generator, and that's how we push the waveform into what we have here. So with that known, we can keep on going. And I made a mistake in this drawing right here, or in my breadboard. So what the correct way is if we move this yellow wire in the same column as this resistor and this blue wire in the same column as this resistor. The reason why I pulled the resistor out, because it used to be right here, now it's located right here. It doesn't matter the column you move it to, you just need to move it to a specific column. That way we can check the input. So we're taking it out of our circuit. We are going to push our waveform into it. That is what the yellow wire is for. The blue wire is to look at our input, because we have output, and the output was from here into here. If we look at the pinouts for analog discovery, we know that this first column right here is going to be our output. Our input. So that's our output for the first part. It's a little bit confusing, but basically we have the output for the first part, which we just looked at as the first column. And this resistor takes that output and pulls it to be an input for the second part with this capacitor right here for the low filter part. So what we're going to do is we're just going to separate this from our circuit and test the input. So the blue wire again is our input. The orange wire is going to be our output. So what we need to do is move it to the output column of the second part. So we're going to take it from our previously placed spot, which was right here, and we're going to put it in the output column. That's the very last column of our op amp. And so it's going to look something like that. Now, so basically we have this orange wire in this column. We have our resistor in this column. And also our blue wire is in this column and our yellow wire is in this column, the same column as our resistor. That way we can test it. We are going to change this amplitude back to 500 microvolts and change it back to a sine wave and see if we need to change it anything else from there. So we can start our supplies like this. It does look like we have some issue, so something is wrong. We're going to change this to 1 volt, and looking at our scope, we have some output. So all we did here was change our channel 1 to be 500 millivolts to match our channel 2, and our wave gen we changed the amplitude to be 1 volt, so we get something a little bit higher. Now we do have some noise still around here, but this looks a lot better. So that is good. This looks great. We've debugged our second part, and now we are going to look at our third part, which is this portion. We have our breadboard here. Now I have modified a little bit just to clean things up a little bit. Some things that I've changed is this capacitor is stretched out a little bit, and we just have this wire going here a little bit cleaner. Everything's a little bit nicer laid out. So what we're doing is we are testing some things. So I'm going to bring this over here, that way we can make a nice drawing. And we're really focusing on this part right here, the last circuit. So this last one is a low pass filter. It has a bunch of gain because of the resistor values that we're going to be using. Now the previous ones are a differential or differentiator with a high pass filter. This middle one is a RC low pass filter. And whenever we test them, just like we did previously, we are going to want to disconnect it from the circuit. So we have its own smaller circuit over here. It's its own little thing. So disconnecting it, we then push in our waveform right here. And then we also have our scope right here to monitor the input. And this is our wavegen. So all of this doesn't matter right now. We have some current flowing through this way, into here, into here. It's going into here. Now this is one of the inputs of our op amp. This is another input of our op amp. I believe this is the positive one, and the positive one is going to ground. And the negative input is going to be the input that we are feeding in right here. So with that known, we can erase this. And the output is this last pin column. So we're taking this output, which is right here, and we're feeding it into the resistor and capacitor that's in parallel. Now it's going to come out of it through this wire. It's going to snake around this way and go back right here. And right here, it's going to basically give negative feedback because it's going into the negative terminal, this column right here, into our op amp right there. And this is just to power the op amp. That's the negative part. So now let's test this. Also the orange wire right here is for our channel 1 scope. So with that known, we can pull up our waveform. We're going to be left with the basic default settings. We're going to change this to 2 Hertz. We want our amplitude to be, we could change it, we want to make it small, so we'll do 500 microvolts. So we'll do UV, and then our offset, we'll just have it at 0 volts. So if we go to our scope, we can see that everything is not okay. So we want to have a solid input right here at 0. That's totally fine. That's for our input. For our output, and if we look at this one more time because this is important, we know that we have our current flowing in this way. And this is a 100 ohm resistor, I believe, and then this resistor up here is 47 kilo ohms. That's the reason for the high gain, because we're using such high resistors. So we want our voltage to be about 1 volt. This is not 1 volt. And we want the peak to be value to be like that. So we need to adjust this. Now our offsets contribute to this, it seems. So if we have 4.25 here, and then we just replace this with like 7, we can see that it does change it a little bit. So everything contributed to this. I'm going to replace this with our 4.25 just to get back there, and we have about 1 volt peak to peak, and that's what we wanted. We're now going to be looking back at the breadboard, and this is not just a picture because I think it's better served if we do it in person like this. So we can see that I've moved everything back. I have put this resistor back into the output of our kind of second stage, and that is here. We have this orange probe, and that's for the channel 1. We're going to be monitoring that output. Now, the blue, we don't need it anymore. This channel 2, we only used it to compare our results, so we can just throw it in ground so it doesn't disturb us. This yellow one as well, we can, because we're not using our wavegen, we can actually turn it off inside of our waveforms, and we can just ground that as well. We don't need it. That's just because my wires are like this, and they're just going to come out if I don't do something with them. So these don't matter anymore. This does. So we want to monitor the output of our entire circuit. So obviously we're going to put it at the output of our final stage. This is going to be our op amp. This is how it's wired. We can see that I've moved all of these wires around just like this. Here's a quick look at it. We have these jumper cables that makes both the bottom and negative, or the top and bottom rails power supply enabled. So we have a grounding that's going through the negative, and then a power that's going to the positive. So we also have these right here. I might change this out. You can see I made it a little bit nicer, a little bit neater. So this is our circuit. Now, here's my error. The actual lab for what we were doing was asking for an infrared transistor. Now, this is a little bit different from if we look at the data sheet, and that should be in the notes linked below the like button, or it will be in the actual lab document. It'll be a PDF download, or it'll be a link to a PDF download. But I had a infrared photo transistor, not an infrared transistor. I guess there is a difference. And basically, when I have this shorter, this black one right here, and there's this longer black one. So if we have the shorter black one, I actually get a result. So if I turn on my supplies right here, this is what it looks like. It's gonna look like this. We'll just wait, we'll just give it a second to kind of level out, let it do its thing. That's just when I move it. And now I'm gonna actually put my finger on top of it. So I put these together like this, and then I put my finger on top of both of them just like this. And if we were to do that, we get what looks like a heartbeat. So it looks something like this. That is my heartbeat. Now, this is very similar to if we are to look in the analog, the Digilant activity. If we look at the graph that they provide, the output looks something like this. So it looks something like this, and if I put my fingerprint or my finger over our sensor, I'll bring it back in a second to just get a good look. That's what it looks like. It's gonna look something like this. So it's pretty similar. It can be seen as far off, but I think it's pretty similar. If we were to just adjust our y-axis, we might get a bigger kind of output. So if we change our range, maybe instead of 1 volt per division, 500 millivolts per division. Actually, that goes a little bit too far. So 1 volt per division is perfect for us to put our finger on, and it's going to have our heartbeat right here. Now, if we change this out, so make sure you turn off your power supplies when you do this. And if I were to put, or take this one out and put this longer one in, remember we have our anode as the longer one and cathode as the shorter one. And we're going to put it, make sure it's in the right columns. So we'll just put it in here like this. And the way I'm gonna do it is I'm just going to lay my finger across it like this. That way it gets all of them. So I'm gonna turn on the supplies, and then I'm going to put my finger across just like this. Now we can see that it just remains kind of a flat line. Even if I change out my finger to my thumb, and I hold it together like this, it's not gonna do anything. It's gonna just remain flat. Now, if we again turn off our power supplies, and then we switch which one this is to the smaller one, which is the photo resistor, and we place this in here, make sure to ground it and put it into power. Turn on our supplies. I'll place my thumb right here. So this is what it should look like. We get what looks like a heartbeat right here. Now, this can change depending on our offset, how much our y-axis, depending on our base. Those settings right there, we could probably adjust it to show more. But this right here looks very similar to what we have up here. So this looks very much like this. Pretty satisfied with the output. Looks great. And I think, I'll have to check with my instructor, but we have completed this lab. We have a peak-to-peak value of about 7 volts. It fluctuates a little bit, but 6 to 8 volts. And that is it for this lab.